What if the celestial body known as Three-Eye Atlas proves to be an unforeseen phenomenon, a momentous cosmic anomaly that fundamentally alters the course of history? Initially, it was characterized as merely another interstellar traveler, a frigid remnant from an unknown origin, drifting inconspicuously past our sun, leaving behind only analytical data and minuscule particles. However, its departure never materialized. Instead, it began to exhibit a deliberate acceleration, not a random drift. Its velocity altered, its luminosity pulsed, hinting at an unseen guiding force. This is precisely when our established mathematical frameworks faltered. The equations ceased to yield coherent results. What was once entirely predictable became utterly inscrutable. Astronomers have labeled it an anomaly. But what if its true nature is something far more profound? What if this represents a one-in-a-billion occurrence, the kind that compels us to reevaluate our understanding of gravity, time, and even chance itself? Remain alert, for tonight you will grasp why an event that might conceivably never recur within the lifespan of our planet appears to be unfolding at this very moment. If this enigma continues to captivate your attention, as it has mine, be sure to engage the like and subscribe buttons to ensure you receive every update as this unfolds in real time. Please share your location, the current time there, and your thoughts on this emerging possibility in the comments section. Furthermore, if you wish to contribute to the expansion of this community, disseminate this video across platforms like X, Facebook, Reddit, or even within your personal group chats. Your support is the driving force that enables us to pursue such compelling narratives. We are profoundly grateful for your unwavering backing. Part 1. The latest breaking anomalies. Envision this scenario. Telescopes synchronized across entire continents. Trajectory projections illuminated on screens within dimly lit control rooms. A sudden expulsion of water vapor emanating from a frozen wanderer situated millions of miles from the sun. Headlines flashing across news feeds proclaiming alien technology. Unexpected acceleration. A phenomenon previously unseen. This is not a work of fiction, it is a present-day occurrence. And it has been assigned a designation, Three-Eye Atlas, an interstellar comet identified in July of the year 2025. It was anticipated to behave like any other fragment of ice and rock we have previously catalogued. Predictable, measurable, and innocuous. Yet, Three-Eye Atlas is defying expectations. And the more we investigate, the more perplexing it becomes. When astronomers first detected this visitor from beyond our solar system, they presumed it would adhere to the established patterns observed with its predecessor, Oumuamua. They believed they understood what signs to anticipate: outgassing, a surge in brightness as it neared the sun, and a trajectory subtly altered by expulsions of sublimating ice. Nothing alarming, nothing that would cause undue concern. However, within weeks of its discovery, the gathered data began to deviate from the initial projections. And now, months later, we are confronted with something that defies logical explanation. Allow me to present a single instance that is bound to send a shiver down your spine. This comet is expelling water at an astonishing rate, akin to a fire hose. This is occurring not in proximity to the sun, where one would expect volatile ices to vaporize, but at a distance of approximately 2.9 astronomical units from the sun. That is nearly 3 times the span between Earth and our star. At such a remove, most comets are inactive, quiescent, and entirely frozen. But Three-Eye Atlas is demonstrably active, extraordinarily so, and the reasons remain elusive to all. The James Webb Space Telescope directed its infrared instruments towards this object and detected an even more peculiar characteristic. The coma, that luminous envelope of gas and dust surrounding the nucleus, is predominantly composed of carbon dioxide, not water, carbon dioxide, and the ratio of carbon dioxide to water stands at approximately 8 to 1. This constitutes one of the highest carbon dioxide to water ratios ever observed in a comet, a record in the entire history of cometary science. Consider this. We have scrutinized hundreds of comets, meticulously cataloged their chemical makeup, and developed comprehensive models. And then, this entity arrives from interstellar space and disrupts the established order. Thus, we face a fundamental dilemma. If this is indeed a comet, a natural celestial body composed of ice and rock, why is it so active so far from the sun? Why does its chemical composition exhibit such extreme characteristics? And if it is not entirely natural, if there exists even a minuscule possibility that it is something else, then what might that be? Some astronomers are beginning to voice a term more commonly associated with financial markets and the study of epidemics: a black swan, an event so rare and unpredictable that it necessitates a rewriting of the rules after its occurrence. Now, I understand your inclination to think, comets are inherently peculiar. Space is replete with outliers. However, consider this. Avi Loeb, an astrophysicist and the same scientist who posited that Oumuamua might be an artificial construct, has highlighted that 3I Atlas exhibits non-gravitational acceleration anomalies that do not conform to standard predictive models. When a comet releases gas, these expulsions exert a slight push, diverting its trajectory. This is entirely normal and anticipated. But 3I Atlas is not accelerating as predicted. Alternatively, it is accelerating, but the forces at play do not correspond to the observed rates of gas expulsion. In either scenario, a fundamental inconsistency exists. And when basic principles of physics no longer align, one is compelled to pose uncomfortable questions. Allow me to illustrate its path. This object is traversing a hyperbolic orbit. This signifies that it originated from interstellar space and will ultimately depart our solar system permanently. It is moving in a retrograde direction, meaning it orbits the sun contrary to the motion of the planets. Its inclination, relative to the ecliptic, the plane in which most planets orbit, is merely about 5 degrees. While this might not seem significant, it is statistically unusual. Most interstellar objects are expected to approach from random angles, yet this one entered our system nearly aligned with our planetary disk, almost as if it had a precise destination in mind. Its perihelion, the point of closest approach to the sun, occurred on October 29th, 2025, merely days ago. At this very moment, as you are absorbing this information, 3I Atlas is completing its closest pass to the sun and commencing its outward journey, with scientists urgently striving to collect every fragment of data before it recedes into the cosmic background. However, the question that should truly occupy your thoughts tonight is this: could this object precipitate a sequence of unforeseen events? Could it already be undermining our fundamental assumptions about what is conceivable? Could it be the initial domino in a chain reaction that we have yet to even imagine? Because if 3I Atlas is indeed a black swan event, then by its very definition, we will only recognize it as such in retrospect, after its repercussions have unfolded. Over the ensuing 2 hours, we will meticulously examine whether 3I Atlas is simply an exotic entity, a statistical anomaly within an infinite cosmos, or if it is subtly and fundamentally reconfiguring the very laws of space. We will explore 8 distinct scenarios, ranging from the plausible to the highly speculative. Some are firmly rooted in the principles of orbital mechanics and observational astronomy. Others venture into realms that will undoubtedly elicit skepticism from the uninitiated, but that is precisely the nature of the subject. A black swan event is not meant to be readily apparent. It is intended to remain unseen until the precise moment it irrevocably alters everything. We will investigate orbital perturbations that could trigger cascading effects for decades to come. We will contemplate fragmentation events that might introduce future hazards. We will consider the possibility of this comet interacting with the Sun in unprecedented ways. We will scrutinize the potential for artificial signals embedded within the pervasive noise. We will delve into atmospheric anomalies, cascades of disclosure, psychological shock waves, and even glitches in reality itself. Moments where the instruments themselves might reveal fundamental fissures in our comprehension of time and space. And here lies an uncomfortable truth. We might already be immersed within this Black Swan event. We may be witnessing its unfolding in real time, misinterpreting it as mere scientific curiosity rather than a potentially catastrophic development, because that is the characteristic modus operandi of such events. They only achieve clarity in hindsight, after the established paradigm has been irrevocably shifted, after the rules have been rewritten, and after it has become too late to implement any preparatory measures. Therefore, let us commence. Let us peel back the layers of understanding. Let us meticulously analyze the data, the speculation, the underlying fear, and the pervasive sense of wonder. Let us articulate the question that few are willing to voice openly. What if Atlas is not merely passing through? What if it signifies the commencement of something we are presently incapable of defining? Part 2. Observed deviations from expectation. Before we embark on an exploration of these anomalies, it is imperative to establish a foundational understanding. We must comprehend what constitutes normal behavior, as the sole method of identifying a deviation is by knowing precisely what is being deviated from. And in the context of interstellar comets, we possess a reasonably clear understanding of anticipated characteristics, or at least we believed we did. As a comet approaches the Sun, solar radiation elevates its surface temperature. This causes ice to sublimate, transitioning directly from a solid state to a gaseous one. This gas then escapes through fissures and vents within the nucleus, carrying along with it minute particles of dust. This phenomenon gives rise to the coma, an incandescent atmospheric shroud, and at times, a tail that extends for millions of miles behind the comet. The streams of gas also function analogously to miniature rocket engines, subtly nudging the comet off its purely gravitational trajectory. This phenomenon is termed non-gravitational acceleration, and it is predictably quantifiable. Based on the comet's proximity to the Sun, its dimensions, and its constituent materials, astronomers can accurately calculate the extent to which it will deviate from a path dictated solely by gravity. Comets also intensify in brightness as they approach the Sun. This increase in luminosity follows a power law relationship. The closer they get, the more active they become, and the brighter they appear. Scientists employ a metric known as the heliocentric distance exponent to characterize this correlation. For the majority of comets, this exponent falls within a specific, established range. If it deviates too far upwards or downwards, it suggests an unusual composition or an atypical behavioral pattern. So that constitutes the baseline. Outgassing intensifies closer to the Sun. Brightness adheres to predictable curves. Non-gravitational forces correspond with observed outgassing rates, and photometric behavior aligns with solar distance. These are straightforward, verifiable, and reliable principles. Now, let us turn our attention to 3I Atlas. At a distance of approximately 2.9 astronomical units from the Sun, it was already exhibiting water expulsion rates, typically observed much nearer to the solar body. Imagine activating a faucet in a deeply frozen environment and observing water flowing nonetheless. That, in essence, is what is occurring here. At such a distance, most comets are dormant. Their surfaces are too cold to facilitate significant sublimation. However, this comet appears indifferent to our established models. The James Webb Space Telescope conducted an analysis of its coma's composition and discovered something truly extraordinary. Carbon dioxide is the dominant constituent. The ratio of carbon dioxide to water is approximately 8 to 1. To provide context, most comets within our solar system exhibit ratios closer to 1 to 10 or 1 to 20. Water typically represents the predominant volatile substance, but this is not the case here. In this instance, carbon dioxide reigns supreme, and the reasons remain unknown. Is the nucleus exceptionally rich in carbon dioxide ice? Did it form in a colder, more carbon-rich region of its parent star system? Or is some other mechanism responsible for releasing the carbon dioxide in a manner we do not yet comprehend? Dust production represents another peculiar characteristic. Observations from the Nordic Optical Telescope have quantified how dust production scales with distance. The power law index determined from these measurements was approximately 3.8, with a margin of error of plus or minus 0.3. This numerical value indicates the comet's sensitivity to solar radiation. A higher index signifies rapid fluctuations in activity, while a lower index suggests more gradual changes. 3I Atlas falls within a recognized spectrum, but it resides at the upper end. It is reacting with considerable intensity to solar radiation, more so than would be anticipated for an object with its presumed composition. Furthermore, there is the matter of polarimetry. When sunlight is scattered by dust particles within the coma, it becomes polarized. The degree and angle of this polarization are contingent upon the size, shape, and composition of these dust grains. Astronomers who observed 3I Atlas noted what they described as extreme negative polarization. This is a technical way of stating that the observed polarization behavior does not align with that of known solar system comets. The phase angle dependence, which describes how polarization shifts as the viewing angle changes, is anomalous and deviates from the norm. Now, let us discuss its trajectory. 3I Atlas is following a hyperbolic orbit characterized by an eccentricity exceeding 1. This signifies that it is not gravitationally bound to the Sun. It will eventually escape. Its inclination relative to the ecliptic plane is approximately 5 degrees, and it is moving in a retrograde direction. This particular combination of orbital parameters is statistically uncommon. The majority of interstellar objects are expected to approach from random directions. The fact that this object entered our system with such near alignment to the plane of the planets could be a mere coincidence. Perhaps. However, coincidences in astronomy frequently mask more profound underlying truths. Perihelion, its closest approach to the Sun, occurred on October the 29th, 2025. Currently, the comet is on its outbound trajectory. On October 3rd, 2025, it passed within an approximate distance of 0.19 astronomical units of Mars. This is a remarkably close proximity, even closer than many encounters with near-Earth asteroids. On November 3rd, it will pass within 0.65 astronomical units of Venus. And in March of 2026, it will approach within 0.36 astronomical units of Jupiter. While these close passes do not pose a risk of collision, they do raise pertinent questions regarding gravitational interactions. Could this object potentially perturb the orbits of smaller celestial bodies? Could it divert an asteroid onto a different path? We will revisit this crucial question at a later juncture. This is where the situation becomes truly perplexing. Despite significant outgassing, and despite the substantial expulsion of water and carbon dioxide from its surface, 3I Atlas does not exhibit the anticipated non-gravitational acceleration. Or, at the very least, the observed acceleration is considerably less pronounced than theoretical models predict. Avi Loeb has pointed out that this implies the nucleus must possess either an exceptionally large mass or an exceedingly high density. If the expelled gas is pushing against a substantial mass, the resulting acceleration will be minimal. Conversely, if the nucleus is small and the outgassing is weak, where does all this expelled water originate? The figures simply do not reconcile. the forces involved do not achieve equilibrium. There is a critical element missing from the equation. The estimations of its size vary considerably. Depending on the assumptions made regarding its reflectivity and composition, the nucleus could range in diameter from 0.32 kilometers to 5.6 kilometers. This represents a substantial degree of uncertainty, and this uncertainty propagates through every subsequent calculation we undertake. If the nucleus is small, the rates of outgassing appear preposterous. If it is large, the absence of significant acceleration becomes equally preposterous. In either scenario, we are confronted with absurdity. Therefore, what are the implications of this discrepancy? If outgassing is expected to propel the object off its orbital path, yet it deviates only marginally, we are left with a few potential explanations. Perhaps the gas jets are perfectly symmetrical, effectively canceling each other out. Alternatively, the nucleus might be rotating in a manner that distributes the propulsive force uniformly. It is also conceivable that the material being ejected moves at such a low velocity that it imparts minimal momentum. Or, just possibly, the nucleus is far denser than anything we have previously encountered. Denser than rock, denser than iron, so dense it compels us to question its fundamental composition. And this leads us to the unavoidable, uncomfortable question: is this merely an unusual comet, or is it the initial indicator of something far more unpredictable? Because if we are unable to explain its behavior using established models, then our models are, by definition, incomplete. And if our models are incomplete, what other critical factors might we have overlooked? Part 3. Media and community reaction. Speculative framing. The scientific community is presently experiencing a notable divergence of opinion. On one side stand the cautious adherents of the establishment, scientists who have dedicated their careers to the study of comets, individuals who place their trust in empirical data, who prioritize peer review, and who generally resist sensationalized pronouncements. On the opposing side are the provocateurs, researchers who are inclined to entertain hypotheses with low probability but potentially high impact, individuals who believe the universe may still hold astonishing surprises. Occupying the space between these two factions is the media, which amplifies the voices from both sides, at times with commendable responsibility, and at other times with a distinct lack of prudence. Tom Statler, NASA's principal scientist for small bodies in the solar system, has publicly stated that 3I Atlas exhibits characteristics consistent with a comet. He has strongly emphasized that the overwhelming body of evidence points towards a natural celestial body, citing water outgassing, dust production, and photometric behavior that aligns with sublimation processes. He maintains that these are all definitive hallmarks of a comet, with no indications suggesting any artificial or unconventional origins. It is simply a fragment of ice from another star system behaving as such fragments are expected to. However, there is also Avi Loeb, the Harvard astronomer who gained widespread recognition after proposing that Oumuamua might be an extraterrestrial light sail. Loeb has been notably vocal regarding 3I Atlas. He has drawn attention to the anomalies in its acceleration. He has questioned the foundational assumptions underpinning our predictive models. And he has strongly urged the scientific community to refrain from prematurely dismissing low-probability hypotheses without thorough investigation. He is not asserting that it is definitively extraterrestrial. Rather, he advocates for investigation, arguing that without inquiry, we can never definitively know. And then we have the media's role. Sensationalist tabloids have featured headlines speculating about disguised hostile alien technology. Major news outlets have embraced the Black Swan framing, characterizing the object as rare and potentially transformative. The Guardian has published articles that carefully balance scientific caution with public intrigue. Live Science has explored the theoretical possibility of artificial origins, presenting it as unlikely but not entirely inconceivable. Scientific American has reported on Loeb's pronouncements, stressing the importance of definitively ruling out exotic explanations through rigorous observation rather than mere conjecture. The Times of India has described 3I Atlas as a rare black swan object and referenced an international observation campaign coordinated by the International Asteroid Warning Network, or IAWN, a consortium of telescopes and space agencies dedicated to the detection and tracking of near-Earth objects. The very fact that they are involved signifies that this object is being treated with a serious degree of attention, not as an immediate threat, but as something meriting close scrutiny. So, why would scientists even entertain narratives involving extraterrestrial technology? Why risk their professional credibility by engaging with such speculation? The reason lies in an asymmetry of consequences. If one chooses to ignore a low probability event, and it subsequently proves to be real, the resultant consequences can be catastrophic. Conversely, if one undertakes an investigation and finds no extraordinary evidence, the primary cost incurred is merely wasted time and resources. This ethical framework is analogous to Pascal's wager, applied to the field of astronomy. The potential cost of being incorrect in this scenario outweighs the potential cost of appearing, in retrospect, to have been overly cautious. However, a more concerning aspect of this framing exists. Unchecked speculation can foster apprehension. It can attract individuals inclined towards conspiracy theories. It blurs the critical distinction between responsible scientific inquiry and irresponsible fear-mongering. When mainstream media outlets begin employing phrases such as alien technology and Black Swan event, they are not merely reporting information. They are actively shaping public perception. They are influencing how the public, and indeed policymakers, react to uncertainty. Consider this scenario. What if 3I Atlas is entirely benign? What if it is simply a comet possessing unusual yet ultimately explainable chemical properties? However, due to the pervasive speculation and the chosen framing, valuable resources might be diverted. Telescopes might be redirected towards this object instead of other critical targets. Debates concerning planetary defense budgets might be initiated. International collaborative efforts might be established around a non-existent threat. And all of this could occur simply because the distinction between prudent caution and unfounded paranoia could not be maintained. Conversely, what if the speculation is indeed warranted? What if there exists even a 1% probability that this object represents something unprecedented? In such a circumstance, choosing to ignore it would constitute negligence, potentially leading to danger, and ultimately, a failure of both imagination and professional duty. Because the very essence of a Black Swan event is its inherent unpredictability. One cannot effectively prepare for it by adhering to established protocols. It necessitates a willingness to contemplate the seemingly impossible. This inherent tension directly influences funding decisions, the allocation of telescope observation time, and the seriousness with which space agencies approach follow-up investigations. If an object is merely categorized as a curiosity, it will receive minimal attention. However, if it is designated as a potential Black Swan event, suddenly, everyone expresses keen interest. Careers can be forged or irrevocably damaged depending on whether the initial excitement is ultimately validated. Furthermore, there is a significant psychological dimension to this phenomenon. Why are individuals so profoundly captivated by this particular object? Why does the concept of an interstellar visitor evoke both a sense of wonder and an underlying dread? Perhaps it serves as a stark reminder of our own cosmic insignificance, the fragility of our current understanding, and the vast expanses of the universe that remain utterly unknown. Or perhaps deep down, we are yearning for something to disrupt the prevailing monotony, yearning for irrefutable proof that we are not alone, or conversely, for confirmation that the cosmos is far stranger than we have ever dared to imagine. The concept of the Black Swan extends beyond mere scientific classification. It is deeply ingrained in our culture. It reflects our collective response to the unknown. Do we dismiss it as insignificant noise? Do we earnestly investigate it as a potential signal? Do we allow fear to dictate our actions? Or do we embrace curiosity? Because once a black swan event has occurred, once the fundamental paradigm has shifted, there is no returning to the previous state. One cannot simply unsee what has been witnessed, nor can one unknow what has been learned. The world is irrevocably altered in its aftermath, and that transformation is permanent. Therefore, the critical question remains. Are we amplifying 3i Atlas into something it is not through excessive speculation? Or are we finally acknowledging, with the seriousness it warrants, the possibility that the cosmos still holds the capacity to surprise us? Because the answer to this question will ultimately dictate how we approach subsequent anomalies, and the ones that follow, and the ones thereafter. To determine if this is genuine concern or mere fanfare, we must first establish a clear picture of what a space black swan would even entail. Without a guiding framework, without definitive parameters, our approach becomes purely speculative, and mere conjecture is insufficient given the potential magnitude of the risks involved. Section 4 delves into defining what such a celestial black swan might be. The concept of a black swan event originates with the philosopher and statistician Nassim Taleb, who employed it to characterize occurrences that are exceedingly rare, inherently unpredictable, and possess profound repercussions. These are events that, in retrospect, appear entirely obvious, yet were completely unforeseeable beforehand. A quintessential illustration of this is the financial crisis of 2008. At the time, experts confidently reassured the public that the economic system was robust, investments were diversified, and leverage was under control, only for the entire structure to crumble. Afterward, the warning signs became starkly apparent, but prior to the collapse, they were perceived as mere background noise. Taleb posited that black swan events share three distinct attributes. Firstly, they fall outside the scope of normal expectations. Nothing in past experience convincingly suggests their possibility. Secondly, they exert an extreme influence, reshaping industries, societies, or fundamental worldviews. Thirdly, despite their unpredictability, human psychology compels us to fabricate explanations post-event, rendering them seemingly explainable and, by extension, predictable. We retroactively impose causality, asserting that we should have foreseen them, yet we did not and, crucially, could not have. So, how do we translate this into the domain of astronomy? What would qualify as a black swan in the cosmic arena? Perhaps a comet that initiates a chain reaction of orbital disturbances, an extraterrestrial object that unveils novel physics, a detected signal that confirms the existence of intelligent life, or a disruption so subtle that its impact only becomes apparent decades later. Allow me to propose a preliminary set of criteria for such an event. A space black swan must demonstrate at least three of the following characteristics. Firstly, unpredictability that surpasses our current predictive models. Not merely unusual or infrequent, but genuinely beyond the operational parameters of existing theories. Secondly, the potential for significant impact on planetary safety, scientific understanding, detection capabilities, or humanity's perception of its cosmic standing. Thirdly, irreversible consequences, such as orbital shifts persisting for millennia, the irretrievable loss of data integrity, or groundbreaking discoveries that render established knowledge obsolete. Fourthly, evidence suggesting intentionality or physical anomalies that defy natural randomness, such as a signal unexplainable by known astrophysical processes, a trajectory correction inexplicably deviating from inertia, or a coincidental timing too precise to dismiss. Now, let us apply these criteria to 3i Atlas. Does it already meet any of them? It is certainly unpredictable in the sense that its observed behavior does not precisely align with our models. However, the question remains whether this deviation is truly beyond our current theoretical capacity, or merely at its periphery, a point of contention. Does it possess the potential for significant impact? Scientifically, yes, as it challenges our existing assumptions. However, from a practical standpoint, it does not pose a direct threat to Earth. Are there irreversible consequences? Not yet. And is there evidence of intentionality? None that we have detected thus far. Consequently, by these specific criteria, 3I Atlas is not currently classified as a black swan, at least not definitively. Nevertheless, it retains the potential to become one. Should it exhibit unexpected behavior, such as fragmenting in an unusual manner, perturbing another celestial body, or if we were to detect a signal, or if any of a dozen other improbable scenarios were to materialize, we would retrospectively deem it a black swan all along. This, then, is the inherent paradox. One cannot identify a black swan before its occurrence. One can only prepare for the possibility, construct systems resilient enough to weather unforeseen events, and foster a mindset that regards the improbable as worthy of diligent investigation. So, what are these potential scenarios? What are the specific pathways through which 3I Atlas could evolve into a black swan? I have identified 8. Some are rooted in established physics, others are purely speculative, and a few verge on the metaphysical. Yet, each represents a distinct form of potential crisis, a unique trajectory from initial curiosity to eventual catastrophe. The first scenario I term orbital domino. A minor gravitational influence leads to a cascade of orbital shifts affecting other objects. For instance, 3I Atlas might slightly perturb an asteroid as it traverses near Mars. This minor alteration in the asteroid's orbit, seemingly insignificant at first, could compound over decades, eventually placing it on a collision course with Earth, undetected because the initial perturbation was not sufficiently tracked. My second proposed scenario is a fragmentation event. The comet breaks apart in an unconventional manner. Perhaps one fragment exhibits directed propulsion, or decelerates contrary to the expected direction of its outgassing. It might display characteristics suggesting internal structure, propulsion systems, or an unexplainable phenomenon. The third scenario is solar disruption. An unusual solar event, such as a coronal mass ejection or a solar flare, might coincide with the comet's closest approach to the Sun with uncanny precision. There could be a feedback loop. Perhaps the comet triggers the solar event, or the timing itself is too statistically improbable to be mere chance. This could lead to widespread satellite failures and communication blackouts, or auroras appearing in unexpected locations. My fourth scenario involves an artificial signal. Telescopes might detect a narrow-band radio pulse, too brief to confirm and too faint to repeat, buried within background noise until sophisticated analysis uncovers it. The ensuing dilemma would be whether to announce such a finding, to pursue further investigation, or to suppress it due to its potentially destabilizing implications. The fifth scenario is an atmospheric anomaly. The comet's passage might trigger or coincide with unexpected disturbances in Earth's upper atmosphere, such as ionospheric spikes, significant GPS signal delays, or off-season auroras. Similar effects might be observed by Mars orbiters, transient yet measurable. The sixth scenario is a disclosure cascade. This could manifest as unofficial leaks, coordinated official statements, or data releases timed with the object's flyby. While potentially benign, it might represent the initial phase of a controlled dissemination of information, a gradual revelation to prepare the public for a more significant, perhaps underlying truth. The seventh scenario, a psychological singularity, arises from widespread public attention, creating a social amplification effect, synchronistic events, heightened anxiety, and a collective conviction that something momentous is about to occur could influence decision-making, policy shifts, funding allocation, and career trajectories, making the object significant not due to its inherent nature, but due to our perceived expectations. Finally, the eighth scenario, a reality glitch, is highly speculative. It posits minor desynchronization of instrumentation, anomalies, impulsor timing, spacecraft telemetry, or atomic clock drift, all aligning with the comet's transit, as if the object is disturbing space-time itself, or exposing a fundamental flaw in our understanding of time. Each of these scenarios poses a unique question. Could a fragment redirect an asteroid centuries from now? Is it plausible that we have already recorded a signal that vanished before we grasped its significance? Could a comet interact with the Sun in ways previously unimagined? Can collective perception manifest as a self-fulfilling prophecy? Some of these possibilities are grounded in scientific principles. Orbital perturbations and fragmentation are well understood phenomena. Others, however, verge on the cinematic or even paranoid. Yet, this is the essence of a black swan. It is not the most probable outcome, but rather the overlooked one. The scenario dismissed as too implausible until it becomes a reality. In the subsequent sections, we will scrutinize each scenario in detail, assessing which remain plausible given current data, which can be definitively ruled out, which are inherently unknowable, and which may already be unfolding undetected. For if even one of these scenarios proves to be genuine, our comprehension of the cosmos will be irrevocably altered. Part 5 presents a preview of these 8 extraordinary possibilities. Let us examine each scenario sequentially, not exhaustively at this juncture, but sufficiently to grasp its essence and appreciate the weight of its implications. Each scenario represents a distinct manner in which the universe could surprise us, and each carries consequences for which we are presently unprepared. Scenario 1, Orbital Domino Sofu, posits that on October 3, 2025, 3I Atlas passes near Mars. It does not collide with anything, but its gravitational field exerts a minute tug on a small asteroid, altering its velocity by a fraction of a meter per second. This seemingly insignificant change, imperceptible in the short term, can, over time, lead to substantial orbital drift due to the chaotic nature of celestial mechanics. Over 10 years, the asteroid's path shifts. After 20 years, it intersects a different orbit. By 30 years, it is on a collision course with Earth, a threat we failed to anticipate because the initial perturbation was not meticulously tracked. Could 3I Atlas initiate such a chain reaction, nudging an object into a future hazardous trajectory? The mathematics suggest it is possible, albeit improbable. Scenario 2, Fragmentation Event, considers that comets routinely fragment due to thermal stress, rotational forces, or structural weaknesses. However, what if a fragment behaves in an anomalous fashion? What if it decelerates unexpectedly, or alters its course against the direction of its outgassing jets? Imagine astronomers detecting a secondary brightening weeks after perihelion, initially presumed to be a fragment. However, upon calculating its trajectory, discrepancies emerge. The fragment's momentum fails to align with the expected ejection velocity, suggesting an external force or an internal propulsion system. While naturally occurring explanations might exist, involving complex internal structures, cavities, pressure differentials, or novel physical mechanisms, the possibility of something more enigmatic cannot be entirely discounted. Scenario 3, Solar Disruption, contemplates the Sun's inherent activity, including regular coronal mass ejections and solar flares. The critical aspect here is the potential for an unusually precise temporal coincidence between such an event and the comet's perihelion passage. If a massive CME were directed precisely at Earth during this period, resulting in satellite failures, power grid fluctuations, and equatorial auroras, scientists would face the challenge of determining whether this was mere coincidence or a causal relationship. Could a comet trigger a solar event? Mainstream astrophysics suggests this is improbable due to the comet's minuscule size relative to the Sun. However, the possibility of unforeseen feedback mechanisms, such as the comet's ionized coma interacting with the Sun's magnetic field in an unexpected manner, cannot be entirely dismissed, especially if our understanding of solar thresholds is incomplete. Scenario 4. Artificial signal examines the continuous scanning of the sky by radio telescopes, which record and filter vast amounts of data, searching for patterns. The scenario proposes that a signal, potentially emitted by 3I Atlas during its perihelion passage, might have been recorded and subsequently overlooked. If the comet were positioned behind the Sun during this event, follow-up observations would be impossible. A signal, initially dismissed as interference, might be unearthed years later by advanced algorithms analyzing archival data, revealing a structured, non-random emission pointing back to that specific time and object. The subsequent dilemma would revolve around whether to publicly announce such a finding, given its potentially destabilizing implications. Scenario 5. Atmospheric anomaly focuses on the Earth's ionosphere, which is sensitive not only to solar wind and cosmic rays but also to charged particles emanating from comets. If 3I Atlas's coma were to interact with Earth's magnetosphere, it could lead to unusual GPS signal delays or detectable spikes in ion density at monitoring stations. Similarly, Mars orbiters might observe transient auroras during the October 3rd close approach. While individually these effects might be subtle and easily dismissed, their simultaneous detection by multiple independent instruments within the same temporal window would elevate coincidence to correlation, demanding an explanation. Scenario 6, Disclosure Cascade, considers the coordinated observational campaign for 3I Atlas, which is publicly known. However, it posits the possibility of clandestine meetings among space agencies, quiet data sharing, and the re-release of archival anomalies during the comet's passage. This would not necessarily imply conspiracy, but rather that the object's unusual nature might warrant a re-examination of past data, potentially revealing discrepancies such as timing residuals in spacecraft telemetry or unexplained trajectory deviations in other missions. While individually inconclusive, these anomalies could collectively foster doubt and initiate a cascade of inquiries. Scenario 7, Psychological Singularity, diverges from purely physical explanations, focusing instead on collective perception. It suggests that a sufficiently widespread belief in an impending event, amplified by social media and taken seriously by policymakers, could lead to the convening of emergency meetings, the redirection of funding, and significant career shifts. The object would gain prominence not due to its inherent properties, but because of our collective conviction. In essence, our beliefs could alter societal reality, leading to consequential decisions and historical shifts, irrespective of the object's actual nature. Scenario 8, Reality Glitch, is the most speculative, venturing into territory often avoided by scientists. It proposes that multiple independent sensors might record subtle timing anomalies during the comet's passage, such as pulsar timing residuals, atomic clock drift, or spacecraft telemetry delays, all aligning with 3I Atlas's perihelion. The question then arises, could ionized dust or charged particles interfere with signal propagation and time distribution systems? Or could this indicate a more profound phenomenon, such as a flaw in our synchronization methods, a ripple in space-time, or a fundamental misunderstanding of our clock's measurements? It is crucial to acknowledge that most of these scenarios are highly improbable, some bordering on impossibility. However, the primary focus is not on probability, but on consequence. A Black Swan event does not announce itself. It resides in the tail of statistical distribution, concealed within background noise, becoming apparent only after its occurrence. In the ensuing discussions, we will examine which scenarios possess supporting evidence, which are empirically testable, which remain purely speculative, and which might already be unfolding without our awareness. For if we are currently experiencing a Black Swan event, only diligent and persistent observation will reveal the truth, or until it is too late. Part 6, covering scenarios 1 and 2, delves into orbital domino and fragmentation event. We commence with the most plausible scenarios, those grounded in established physics, which eschew exotic hypotheses or conspiratorial interpretations. If 3i Atlas is destined to surprise us, it is most likely to do so in a manner that is subtle, delayed, and embedded within the intricate calculations of orbital mechanics. The orbital domino scenario is a particular concern for planetary defense scientists, not due to its likelihood, but because its consequences escalate over time, rendering intervention impossible by the time the problem is recognized. This scenario unfolds as 3i Atlas traverses the inner solar system. As it passes by planets and large asteroids, its gravitational field exerts a almost negligible tug. However, orbits are inherently chaotic systems, highly sensitive to initial conditions. A minuscule alteration in velocity can result in a significant positional change over decades. On October 3, 2025, 3i Atlas passed within approximately 0.19 astronomical units of Mars, a distance of roughly 28 million kilometers. For perspective, the Moon is only 384,000 kilometers from Earth. This was, by astronomical standards, a relatively close encounter. Did it perturb any objects? It almost certainly did. Mars possesses two small moons, Phobos and Deimos, whose orbits are already unstable over geological timescales. A passing celestial body could impart a slight nudge. Would we detect this immediately? Probably not. The changes would be subtle, but over years these deviations would accumulate. Furthermore, Mars hosts a population of co-orbital asteroids, known as Trojans, which are gravitationally stabilized at its Lagrange points. However, this stability is relative, and a perturbation could dislodge an asteroid from its Lagrange point, rendering its trajectory unpredictable. It could drift inward towards Earth, outward towards the asteroid belt, or enter a resonant interaction with Jupiter that amplifies its orbital eccentricity. Let us consider the quantitative aspect. If we assume 3i Atlas possesses a mass of 10 to the power of 14 kilograms, comparable to that of a mountain or a small comet nucleus, its gravitational influence at a distance of 0.22 astronomical units would be exceedingly small. Yet, small does not equate to zero. Gravitational force diminishes with the square of the distance, but it never truly vanishes. Every celestial body in the solar system exerts a force on every other body, and these forces sum up. Now, imagine an asteroid with a semi-major axis of 2 astronomical units, situated in the main asteroid belt, with an orbital period of approximately 3 years. If 3i Atlas were to perturb its velocity by a mere 1 millimeter per second, a seemingly inconsequential amount, over 10 orbital periods, or 30 years, this translates into a positional deviation of hundreds of kilometers. Should that asteroid's trajectory eventually intersect Earth's orbit, those hundreds of kilometers could represent the critical difference between a near miss and a catastrophic impact. Planetary defense networks diligently track near-Earth asteroids, cataloging their orbits and predicting close approaches. However, they do not monitor every single asteroid. Those that are too small or too dim elude detection. Crucially, they do not typically account for perturbations caused by interstellar visitors, which, until the discovery of Oumuamua, were considered purely hypothetical. Now that they are a confirmed reality, they possess the potential to alter celestial orbits, necessitating their inclusion in our calculations. Therefore, the pivotal question is, could 3I Atlas have nudged an object into a future hazardous trajectory? The answer is that we do not possess sufficient data. We lack complete orbital information for every minor body in the solar system. We lack the computational power to model every conceivable perturbation, and we lack the telescopic coverage to detect subtle shifts in trajectories. The vast gaps in our knowledge are precisely where black swans tend to lie hidden. Now, let us address the fragmentation event scenario. Comets frequently fragment. It is one of their most common behaviors. Thermal stress induced by solar heating causes the nucleus to fracture. Rotational forces generate centrifugal stress, pulling apart weakly bound material. Sublimation of volatile ice beneath the surface can create internal pressure, leading to the expulsion of material fragments. We have observed numerous cometary fragmentations. Shoemaker-Levy 9 famously broke into multiple pieces before impacting Jupiter in 1994. Comet Schwarzmann-Wachmann 3 has undergone repeated fragmentation over decades. Consequently, fragmentation in itself is not an anomalous occurrence. The anomaly arises if the fragmentation behavior is unusual. What if a fragment does not behave as dictated by physics? Consider this. 3I Atlas is actively outgassing, with jets emanating from its nucleus imparting momentum. When a fragment separates, it should inherit the parent body's velocity, augmented by the ejection velocity from the breakup event. We can calculate and predict the expected brightness, trajectory, and subsequent evolution of such a fragment. However, what if a fragment deviates from these predictions? What if its behavior cannot be explained by outgassing alone? This would be highly unusual, though not entirely impossible. It would necessitate invoking internal structural complexities, such as cavities channeling gas in specific directions, or asymmetric tumbling that generates unexpected thrust. It might also involve a fragment composed primarily of dust, with minimal ice content, resulting in weak but present outgassing. Alternatively, it could point to an unknown mechanism, a propulsion effect embedded within the physics of cometary activity, or, in its most extreme interpretation, suggest an element of directed motion, implying something internal guiding its path. I am not asserting this as a high probability, but rather stating that if a fragment were to exhibit such behavior, we would be compelled to consider it. Has 3I Atlas fragmented? As of its perihelion passage on October 29, 2025, there have been no confirmed reports of fragmentation. However, this does not preclude the possibility of future fragmentation, as comets often break apart during or immediately after perihelion when solar heating is at its peak. Subsequent observations over the coming weeks will be critical in assessing this. Should luminosity abruptly surge, if numerous constituents manifest within imagery, if a course exhibits unforeseen diversions, these would serve as indicators. And herein lies the disquieting aspect. If a fragment were to display aberrant behavior, how would we embark on its examination? Telescopes possess a finite capacity for resolving granular detail. Spectroscopy can ascertain composition, yet not structural configuration. Radar might ascertain rotational velocities and surface characteristics, but solely if the fragment is sufficiently proximate. And if it is receding from the Sun, it is concurrently moving away from Earth. With each passing day, it diminishes in brightness, rendering observation increasingly arduous. Ultimately, it vanishes into the cosmic background radiation, leaving us with piecemeal evidence, incomplete measurements, and unresolved queries. Could a fragment then sow the seeds for future peril? Might it drift into a protracted orbital path, returning centuries hence? Could it influence another celestial body? Could it carry within it information regarding the parent object's structure, knowledge we shall never recover? The answer to all these is affirmative. fragmentation is inherently unpredictable. It introduces novel variables into an already capricious framework, and every new variable represents a potential avenue for surprise. Allow me to present a hypothetical temporal progression. Envision a fragment detaching itself in November of 2025. Its faintness precludes immediate detection. It drifts. Over a period of 5 years, its orbital path undergoes transformation. By the year 2030, it is intersecting the orbital path of a near-Earth asteroid. By 2040, that asteroid's trajectory has undergone a subtle alteration. By 2060, the asteroid is on a collision course with a constellation of satellites. And no one attributes this to Three-Eyed Atlas because the chain of causation is excessively protracted, exceedingly indirect, and thoroughly obscured by ambient interference. This is the orbital domino effect. This is the apprehension that keeps orbital dynamicists awake at night. For while orbital mechanics are theoretically deterministic, they are practically chaotic. One can ascertain trajectories with remarkable exactitude over brief intervals. However, across decades, across centuries, minute uncertainties escalate into significant divergences, and that which cannot be foreseen cannot be averted. So what is the judgment concerning these two scenarios? Are they plausible? Yes. Are they probable? No. Do they represent potential Black Swan events? Absolutely. Because the impact is delayed, the causal link is obfuscated, and by the time the repercussions become apparent, the initiating event is relegated to antiquity. We would possess no means of tracing it back, no capacity to declare that this occurred due to Three-Eyed Atlas. It would simply be another asteroid, another fragmentation, another perturbation, lost within the cacophony of a disordered solar system. Yet, if we are earnest in our pursuit of planetary defense, if we are serious about enduring survival in the long term, we must acknowledge these possibilities. We must track extraterrestrial visitors not merely during their transit, but subsequently. We must model their gravitational influence on lesser celestial bodies. We must remain vigilant for fragmentation and meticulously characterize any resulting fragments. For the universe operates independently of our models and our presumptions. It simply proceeds according to its own inherent laws, and we must either adapt or face the repercussions. Part 7. Scenarios 3 and 4. Solar disruption. Concurrent with an artificial signal. We now enter a domain that causes most scientific minds discomfort. Not due to physical impossibility, but rather because it necessitates coincidences, temporal alignments, and correlations that could be serendipitous, but appear remarkably precise. And humankind exhibits a pronounced fallibility in assessing coincidence. We perceive patterns where none exist. We infer causality from correlation. We construct narratives that resonate with truth, even when they lack factual basis. However, occasionally, coincidences are not random. Occasionally, timing holds significance, and sometimes the universe presents us with an unexpected challenge that demands an explanation. Therefore, let us examine solar disruption. The notion that Three-Eyed Atlas's closest approach to the Sun might coincide with, or even instigate, solar activity that impacts Earth. The Sun is a system characterized by inherent disorder. Its surface churns with convection. Its magnetic field becomes convoluted and entangled. Every 11 years, the magnetic field undergoes polarity reversal, driving the solar cycle. During solar maximum, sunspots proliferate. Coronal mass ejections occur with increased frequency. Solar flares erupt with energies equivalent to billions of atomic detonations. And all of this activity propels radiation and charged particles into the void. When a coronal mass ejection impacts Earth, it compresses our magnetosphere. Charged particles are channeled along magnetic field lines towards the poles. They collide with atmospheric atoms, generating auroras. If the coronal mass ejection is sufficiently powerful, It can induce currents within electrical grids, leading to the failure of transformers. It can disrupt satellite operations. It can precipitate radio blackouts. The Carrington event of 1859 represented the most formidable solar storm in recorded history. Telegraph systems ignited. Auroras were visible even at the equator. Should a comparable event transpire today, the economic repercussions could amount to trillions of dollars. Thus, solar activity is a tangible and formidable force, unpredictable on short timescales. We can forecast the general solar cycle and predict broad trends, but we cannot precisely anticipate the moment a coronal mass ejection will erupt or its intended trajectory. The system is far too complex. Now, the pertinent question arises: could a comet interact with the Sun in a manner that either triggers or intensifies solar activity? Mainstream astrophysics posits a negative. The comet is too diminutive. Its mass is inconsequential compared to the Sun's. Its gravitational influence is negligible. Its magnetic field, if it possesses one at all, is trivial. There exists no plausible mechanism by which a comet could exert influence upon the Sun. But what of secondary effects? What about the comet's ionized coma? As Three-Eyed Atlas approached its perihelion, its outgassing generated a cloud of ionized gas and dust. This cloud exhibits electrical conductivity. Could it engage with the Sun's magnetic field? Could it establish a feedback loop? Could it act as a catalyst for instabilities that were already developing within the solar corona? I am not asserting its likelihood. I am stating that it is not demonstrably impossible. And if solar activity were to surge during the perihelion window, if a significant coronal mass ejection were to erupt on October 29th or 30th, and if Earth were to experience unusual auroras or satellite disruptions within that precise time frame, we would be compelled to question whether it was mere coincidence. Allow me to verify. Were there any notable solar events around October 29th, 2025? Any coronal mass ejections? Any solar flares? Any geomagnetic disturbances? If such events occurred, the temporal correlation would be striking. If they did not, then this scenario loses credibility. However, the absence of an event does not render the scenario impossible. It merely signifies that it did not transpire on this particular occasion, because the inquiry is not solely whether it occurred, but whether it could occur, and whether we would recognize it if it did. Now let us transition to the artificial signal. This is the scenario that elicits eye rolls from skeptics, the scenario that invites derision, yet it is also the scenario with the most profound implications. Because if it is genuine, if Three-Eyed Atlas is something other than a naturally occurring comet, everything changes. SETI, the search for extraterrestrial intelligence, has been systematically surveying the cosmos for decades. Radio telescopes are attuned to narrowband signals. Optical telescopes search for laser pulses. Sophisticated algorithms sift through noise, seeking discernible patterns. And thus far, no definitive discovery has been made. The WOW signal of 1977 remains unexplained but unreplicated. Fast radio bursts have been attributed to astrophysical phenomena, likely originating from magnetars. Every potential signal either dissolves into background noise or is accounted for by natural processes. However, here is a crucial point. SETI operates under the assumption that signals will be continuous or repetitive. A civilization broadcasting intentionally would seek to be detected. They would transmit for extended durations. They would target promising stellar systems. They would utilize frequencies that penetrate interstellar dust. All of this is logical if one aims to communicate across light years. But what if the objective is not broadcasting? What if the purpose is transit? What if it is a probe transmitting only during perihelion when solar conjunction offers concealment? What if its signal is intentionally designed to be ambiguous, weak enough to be dismissed as interference, brief enough to evade confirmation, yet structured sufficiently to be noticed by anyone scrutinizing closely? and only if they are indeed looking closely. Imagine three-eyed Atlas emitting a pulse on October 29th. A narrow-band emission at 1.42 gigahertz, the hydrogen line, a classic SETI frequency, lasting for 3 seconds. The signal strength barely exceeds the ambient noise. Telescopes would record it, but the data would be classified as radio frequency interference, human-generated, terrestrial in origin, filtered out by standard algorithms, and subsequently disregarded. Years later, an analyst processes archival data through a novel machine learning algorithm. This algorithm is unburdened by human biases. It solely seeks patterns and identifies one. A brief, structured pulse, demonstrably non-random, originating from the vicinity of three-eyed Atlas during its perihelion passage. But by then, the object would have traversed beyond Jupiter, fading into obscurity, leaving no avenue for follow-up, no means of verification, no way to definitively rule it out. Would we disclose it? Would we publish? Or would we bury it because the implications are inherently destabilizing? If it is genuine, if it is artificial, then we are not alone. We have been visited, and we initially failed to recognize it. This then raises disconcerting questions about the multitude of other signals we may have overlooked, the number of other visitors we have disregarded, and the extent of our own blindness. Conversely, if it is not genuine, if it is merely noise, then announcing it would incite panic, erode trust in scientific endeavors, fuel conspiracy theories, and divert resources from legitimate research. Thus, the decision transforms from a scientific one to a political one. Do we disseminate the truth and risk chaos, or do we withhold information and risk accusations of a cover-up? This is precisely why the artificial signal scenario is so fraught with peril. It transcends mere detection. It encompasses response, and response is predicated upon belief, and belief, in turn, is contingent upon evidence. And in this particular instance, the evidence may be equivocal, incomplete, and susceptible to myriad interpretations. And it is within interpretation that objectivity perishes. Therefore, the fundamental question remains: if a signal were detected, would you desire to be informed? Even if it could not be definitively confirmed, even if it might prove erroneous, because while ignorance may offer comfort and certainty may be reassuring, ambiguity is maddening, and sometimes, ambiguity is all that is available. Part 8. Scenarios 5 and 6. Atmospheric anomaly and disclosure cascade. Let us now shift our focus from the vastness of deep space to something closer to home. Earth's atmosphere, specifically the ionosphere. This tenuous layer, situated between altitudes of 100 and 1,000 kilometers, is where solar ultraviolet radiation ionizes atmospheric atoms, creating a plasma. This layer is paramount for radio communication, as it reflects certain frequencies, enabling signals to propagate beyond the horizon. It also influences GPS functionality. Satellites transmit signals through the ionosphere to ground-based receivers, but the ionized plasma introduces delays in these signals. The magnitude of this delay is contingent upon the electron density. Consequently, GPS systems continuously monitor ionospheric conditions and apply corrections. The ionosphere is highly susceptible to solar activity. When the sun emits a flare or a coronal mass ejection, the associated charged particles interact with Earth's magnetic field, generating disturbances. These disturbances manifest as auroras and also cause fluctuations in electron density. GPS signals experience reduced accuracy, and radio communications degrade. In severe instances, satellites can sustain damage. However, the ionosphere is also responsive to other phenomena. Meteor showers, for example. When Earth traverses a stream of debris, thousands of meteors incinerate in the upper atmosphere. The vaporized material becomes ionized, forming transient layers of elevated electron density. These layers can reflect radio waves in unconventional ways and can induce brief disruptions in satellite signals. Thus, the question arises: Could Three-Eyed Atlas have impacted Earth's ionosphere? Not through direct collision. It was not destined to strike us, but rather through its coma, the cloud of ionized gas and dust trailing behind it. Could that cloud have intersected Earth's magnetosphere? Could it have generated a transient disturbance? The answer hinges on the geometric arrangement. Three-Eyed Atlas reached its closest proximity to Earth in late September or early October, at a distance of approximately 1.2 astronomical units, which translates to roughly 180 million kilometers. This distance is too great for direct interaction. However, the coma extends far beyond the nucleus, and the ion tail, propelled by the solar wind, can stretch for millions of kilometers. Could that tail have brushed against Earth's magnetosphere? Could charged particles originating from the comet have been funneled down magnetic field lines? I lack the specific data to confirm this. I am uncertain whether ionospheric conditions were being monitored with particular focus during that temporal window. However, if they were, and if ground-based receivers or satellites detected anomalous spikes in electron density, if GPS signals exhibited unusual delays, and if any of these occurrences correlated with the comet's passage, it would be noteworthy. Not conclusive, but certainly interesting. Furthermore, there is Mars. On October 3rd, Three-Eyed Atlas passed within 0.19 astronomical units of Mars, a significantly closer proximity than its passage by Earth. Mars is equipped with orbiters, rovers, and various instruments. Could any of these have detected atmospheric effects? Mars possesses a tenuous atmosphere, but it does have an ionosphere and experiences auroras, driven not by a global magnetic field like Earth's, but by localized magnetic anomalies. If the comet's coma interacted with Mars's ionosphere, if orbiters detected transient glows or ion spikes, that would be a significant observation. Again, I do not possess the data. Perhaps the data exists, possibly residing in an archive, awaiting analysis by someone. Or perhaps no one was actively looking, as why would they? Three-Eyed Atlas is, after all, a comet, presumed to be inert and non-threatening. Therefore, instruments might not have been directed appropriately, or the data might not have been flagged as significant. The anomaly, if it exists, might be concealed within the noise. This is the frustrating characteristic of Black Swan events. One does not know where to direct their attention until after the event has occurred. By that juncture, the opportune moment has passed, the data has been archived, and public attention has shifted elsewhere. Now, let us discuss the disclosure cascade. This scenario pertains less to the realm of physics and more to the domain of information dissemination, focusing on how space agencies communicate, what information is made public versus what is withheld, and the temporal gap between observation and official announcement. The International Asteroid Warning Network orchestrated an observational campaign for Three-Eyed Atlas. This is a public endeavor, involving multiple telescopes and numerous countries sharing data. Such a degree of coordination is standard practice for objects of particular interest and does not inherently imply conspiracy. Rather, it signifies scientific collaboration. However, the situation becomes more complex. What if that collaboration revealed something unexpected? What if telescopes detected an anomaly? Not necessarily a dramatic one, nor definitive proof of anything specific, but sufficient to warrant a more thorough examination of archival data. Sufficient to justify discrete meetings. Sufficient to initiate internal deliberations regarding the appropriate framing of the findings. Imagine this scenario. During the observational campaign, an inconsistency is noted in spacecraft telemetry. Perhaps a Mars orbiter recorded a minor timing deviation during the close approach on October 3rd. The deviation might fall within acceptable error margins, yet it is present and coincides with the comet's passage. Consequently, other data sources are scrutinized. Telemetry from additional missions is retrieved. and further deviations are identified. These deviations are subtle and minor, yet they exhibit a correlation. Individually, none of these findings are conclusive, nor do they definitively prove anything. However, their collective nature is peculiar. Peculiar enough for someone to draft a memorandum. Peculiar enough for a working group to be formed. Peculiar enough for data to be re-released with updated calibration parameters. And if one is observant, if one is actively seeking patterns, such a progression might become noticeable. One might perceive the initial stages of a cascade unfolding. I am not asserting that this specific sequence of events transpired. I am illustrating how disclosure might operate in the 21st century. Not through a dramatic press conference or irrefutable evidence, but through a gradual unveiling of information, a series of minor revelations. Each revelation, standing alone, is plausible and explicable, but collectively they form a pattern. This pattern suggests that something was observed, something was discussed, and something was deemed significant enough to warrant a reevaluation of existing assumptions. And here's the critical aspect. If such a cascade is indeed underway, we are unlikely to recognize it in real time. We will only comprehend it in retrospect, when someone meticulously connects the disparate pieces of information, when the chronological sequence becomes clear, when the archived memos, data releases, and confidential workshops are compiled into a coherent narrative. By that point, the precise moment of disclosure will be impossible to pinpoint, as it was not a singular event, but rather a protracted process, and processes remain imperceptible until their completion. Therefore, the question arises, are we currently experiencing a disclosure cascade? Are space agencies engaging in quiet coordination? Are archival anomalies undergoing reevaluation? Are meetings taking place behind closed doors? Perhaps, perhaps not. But the very fact that we cannot ascertain this with certainty underscores the central point. Because Black Swan events thrive in ambiguity. They exist in the spaces between raw data and its interpretation, between initial observation and subsequent announcement. And regrettably, by the time an announcement is made, the event itself may have already concluded. Part 9. Scenarios. 7 and 8. Psychological singularity and reality glitch. We now venture into the most peculiar territory, exploring scenarios that deviate from the purely physical and delve into the realms of perception, consciousness, and the human response to enigmatic phenomena. Because at times, the impact of an event transcends the physical and becomes psychological, social, a reflection of how our beliefs shape our perceived reality. Psychological singularity posits that collective attention can generate consequences irrespective of the object's intrinsic nature. Consider historical precedents. During the appearance of Halley's Comet in 1910, widespread panic ensued. Newspapers published alarming accounts of Earth traversing the comet's tail. Entrepreneurs capitalized on this fear, marketing comet pills purportedly offering protection against poisonous gases. In reality, there was no genuine danger. The comet's tail is so diffuse that it poses no threat whatsoever. However, the pervasive belief in imminent peril engendered tangible societal repercussions, anxiety, irrational behavior, and disruptions in financial markets. The event gained significance not due to its physical properties, but because of the collective human response it elicited. Or take the Y2K bug, the Millennium Bug. Computers utilized two-digit year representations. Programmers warned of systemic failures when the year transitioned from 1999 to 2000. Billions were allocated to system remediation efforts. Contingency plans were meticulously drafted. Some individuals amassed stockpiles of provisions. And when midnight arrived, no catastrophic events occurred. Most systems functioned without issue. However, the preparatory measures, the prevailing fear, and the collective reaction itself had tangible consequences. Resources were reallocated, Careers were advanced, and entire industries underwent strategic pivots. So, what if Three-Eyed Atlas precipitates a comparable phenomenon? What if speculation escalates? What if media coverage intensifies? What if a critical mass of individuals begins to believe that something significant is about to occur, not based on verifiable evidence, but on the sheer momentum of the narrative? Because the story resonates as truthful, because uncertainty is uncomfortable, and humans possess a profound desire for resolution. Envision this. Social media platforms erupt with speculative theories. Online forums become abuzz with discussion. Hashtags surge in popularity. Some individuals claim to have experienced prophetic dreams related to the comet. Others report synchronicities, meaningful coincidences seemingly linked to the date. Scientific experts issue statements intended to allay public apprehension, but these pronouncements are measured and cautious. They employ phrases such as, "no evidence of danger," rather than a definitive, "absolutely safe." This subtle linguistic hedging, this inherent caution, is often interpreted as doubt, as an indication of concealed knowledge, as confirmation that vital information is being deliberately withheld. Policymakers begin receiving urgent calls. Journalists intensify their inquiries. Congressional aides request detailed briefings. And suddenly, space agencies find themselves compelled to respond, not because the comet poses a genuine threat, but because the perception of threat has acquired significant momentum. And that momentum in turn generates real-world consequences. Budgets are reallocated, telescope observation time is reassigned, and emergency protocols are reviewed. These actions are taken not in response to concrete data, but as a consequence of prevailing belief. And here lies the recursive paradox. Once these repercussions materialize, once resources are diverted, once the celestial object becomes the focal point of international attention, it assumes objective significance, not based on its inherent nature, but on what humanity has collectively rendered it. The belief itself, in essence, creates the reality. The narrative takes on a life of its own, becoming self-validating. Later, when historians examine this period, they will likely point to Three-Eyed Atlas as a significant event, citing the ensuing policy shifts, the influx of resources, and the cascade of consequences. However, they may overlook the true mechanism of its importance, which was not intrinsic but rather a product of social construction, engineered through collective apprehension. This refers to a psychological tipping point, a moment when the sheer volume of attention surpasses the available information, when conviction eclipses empirical validation, and when the representation of reality supplants reality itself. The most disconcerting aspect is the inherent difficulty in preventing such a phenomenon, as any attempt at mitigation necessitates communication. Communication, in turn, amplifies the narrative. A lack of response is interpreted as deliberate concealment, while openness is seen as confirmation of suspicion. There is no guaranteed victory, only the management of fallout. Now, let us address the concept of a reality glitch, a scenario that delves into metaphysical considerations. This posits that Three-Eyed Atlas could manifest or engender anomalies within the very framework of observation, impacting our perception of time, the synchronization of our instrumentation, and the coherence of data streams. Contemporary astronomy relies heavily on precise temporal measurements. Spacecraft transmit signals that are meticulously time-stamped. Pulsars emit regular signals serving as cosmic timekeepers. Atomic clocks on Earth are synchronized with GPS satellites. All these systems operate on the assumption of a uniform temporal flow, predictable clock rates, and a consistent universal timeline. But what if these systems experience disruptions? What if, under specific circumstances, timekeeping mechanisms fall out of sync? What if numerous independent instruments register minute discrepancies within the same time frame? These could manifest as microsecond offsets or nanosecond residuals, all coinciding with the perihelion passage of 3I Atlas. Is this physically conceivable? Potentially. Ionized plasma can influence signal propagation. Charged particles can interfere with electronic systems. Extreme gravitational fields can induce relativistic time dilation. However, 3I Atlas is not characterized by extreme properties. Its mass is negligible, and its gravitational influence is insignificant. There is no apparent mechanism by which it could impact timekeeping on Earth or in spacecraft. This is unless there is an overlooked factor. This could involve the comet's coma generating an electromagnetic environment that subtly interacts with our instruments. Alternatively, the timing discrepancies might be real and measurable, but fall below our current detection thresholds until specifically sought out. Consider a scenario where a statistical analysis is performed on pulsar timing data from October 2025, with the aim of identifying gravitational wave signals. This would involve comparing arrival times from multiple observatories, potentially revealing an anomaly. A cluster of residuals, minor deviations from expected values, all occurring within the same week, the week of the perihelion. While individually these deviations might be within acceptable noise margins and appear insignificant, collectively they could form a discernible pattern. Similarly, imagine spacecraft telemetry logs exhibiting timestamp anomalies. Orbiters around Mars, probes near Jupiter, and ground-based receivers might all record signals that arrived fractionally earlier or later than anticipated. Again, these deviations would be within error margins, but demonstrably correlated and synchronized, as if some phenomenon affected signal propagation across the solar system during that specific period. What would be the implications of such findings? Could it be an instrumentation error? Certainly. A calibration issue? Absolutely. Random noise that happens to align coincidentally? Yes. Or could it suggest that our comprehension of time measurement is incomplete? That there are environmental influences we have not yet accounted for? That an interstellar object traversing our local space generates disturbances beyond our current modeling capabilities? I am not asserting that this occurred. Rather, I am exploring the potential meaning if it were to transpire. If timing anomalies were detected and demonstrably linked to 3I Atlas, that would be an extraordinary revelation. It would not constitute proof of artificiality, but would confirm that the universe retains its capacity for surprise. It would underscore that our instruments, our models, and our assumptions are perhaps less robust than we perceive. This aligns with the essence of a Black Swan event, not the prediction of the unpredictable, but the acknowledgement of its existence. It signifies that systems possess a greater fragility than is apparent, that infrequent occurrences are more common than theoretical frameworks suggest, and that their impact can be irrevocable. Therefore, we must ascertain which of these hypothetical scenarios represent reality, which remain plausible, and which are definitively refuted by forthcoming data. The narrative of 3 Atlas is still unfolding. The only means to determine if we are within a Black Swan event is through continuous observation, persistent measurement, and ongoing inquiry until clarity emerges, or until it is too late for it to matter. Part 10. The pervasive mystery. What if its influence is already altering our understanding? Let us take a step back and evaluate. We have examined 8 distinct scenarios, ranging from those grounded in orbital mechanics to highly speculative and even bordering on paranoid propositions. It is now imperative to organize these possibilities, assessing their plausibility, potential impact, and any supporting evidence, however tentative. Without a structured framework, we risk merely cataloging anxieties, and anxieties devoid of rigorous analysis are ultimately unproductive. Therefore, let us envision a straightforward matrix. For each scenario, we shall assign a rating of plausibility: low, medium, or high. We will then evaluate the potential impact on scientific understanding, risk assessment, and paradigm shifts. Finally, We will note any existing evidence, not as definitive proof, but as indications, observations that do not conclusively rule out the scenario. Orbital domino effect, plausibility, medium. We acknowledge that gravitational perturbations occur, and that orbits can exhibit chaotic behavior over extended periods. We also know that 3I Atlas passed in proximity to Mars and is projected to approach Venus and Jupiter. Potential impact, high. A delayed cascade of gravitational influences could precipitate future collision risks decades hence. Evidence, none identified to date. However, the absence of evidence does not equate to evidence of absence, particularly given the extended timescales and subtle nature of the perturbations. Fragmentation event, plausibility, medium. Cometary fragmentation is a recurring phenomenon. The occurrence of an anomalous fragment is not improbable. Potential impact, medium to high, contingent on the fragment's subsequent behavior. If it exhibits directed motion, that would constitute a paradigm-altering development. Evidence, no confirmed fragmentation has been observed as of the perihelion passage, though ongoing follow-up observations are being conducted. Solar disruption, plausibility, low. There is no known mechanism by which a comet could instigate solar activity. Potential impact, high. A significant coronal mass ejection during the perihelion period would profoundly affect Earth's infrastructure. Evidence, a review of solar activity logs for late October 2025 would be necessary. If a CME occurred, the temporal correlation would be striking. Conversely, its absence would significantly diminish the credibility of this scenario. Artificial signal, plausibility, very low. This scenario necessitates extraordinary assumptions. Potential impact, extreme. Confirmation of extraterrestrial intelligence would fundamentally rewrite human history. Evidence, none publicly acknowledged, though it is possible that archival data has not been exhaustively analyzed with this particular hypothesis in mind. Atmospheric anomaly, plausibility, low to medium, dependent on whether the comet's coma intersected Earth or Mars' magnetosphere. Potential impact, low to medium, suggesting unexpected particle interactions. Evidence, unknown. This would require an examination of ionospheric monitoring data and Mars orbiter logs from early October. Disclosure cascade, plausibility, low to medium. Coordination among entities is typical. Concealment of anomalous phenomena would imply deliberate withholding. Potential impact, medium. This could erode public trust in space agencies and suggest prior unannounced detections. Evidence, circumstantial. The IWN campaign is public. Further investigation into other data releases would be warranted. Psychological singularity, plausibility, medium. Social dynamics are inherently unpredictable. Consequences may be driven by belief rather than historical fact. Potential impact, medium. This could lead to real-world policy shifts, changes in funding allocations, and heightened public anxiety. Evidence, observable in media coverage and social media trends, to a degree already present. Reality, glitch, plausibility, very low. This scenario requires an understanding of unknown physics or pervasive systematic instrumentation errors. Potential impact, extreme. This would challenge fundamental assumptions regarding time measurement and signal propagation. Evidence, none. This would necessitate in-depth archival analysis of timing data from multiple independent sources. What then can we glean from this assessment? The majority of scenarios possess a low probability of occurrence. Several have plausible underlying mechanisms but lack supporting evidence. A few, such as the psychological singularity, are already manifesting in subtle ways, and others, like the orbital domino effect and fragmentation, remain genuinely possible over extended time frames. However, a more profound question arises. If 3I Atlas is sufficiently unremarkable, if it is merely a comet with unusual, space agencies monitor solar activity, but they do not typically correlate it with the passages of small celestial bodies. Our systems are compartmentalized, specialized, developed for known threats rather than unforeseen events. Consequently, should astronomers adopt a default stance of treating interstellar visitors as potential black swans? Should every Oumuamua, every Borisov, every 3I Atlas warrant a comprehensive suite of observations, including radio scans, infrared spectroscopy, radar imaging, photometry, and trajectory monitoring for years post-perihelion? Such an undertaking would be costly and necessitate extensive coordination, potentially diverting resources from other research endeavors. But what is the cost of inaction? What is the cost of overlooking a potential signal due to insufficient observation? What is the cost of disregarding a perturbation that could escalate into a significant threat decades later? The risk-reward calculus is asymmetric. The downside of excessive caution is resource wastage. The downside of insufficient caution is catastrophic. And here lies the uncomfortable truth. We may already be immersed within such an event. The black swan might be unfolding gradually and subtly, in ways that will only become apparent once it has reached completion. This is characteristic of such events. They do not announce themselves, nor do they await confirmation. They simply occur, and we subsequently scramble to comprehend them. Therefore, what are the critical decision points? What measurements remain significant? Post-perihelion brightness evolution. Is its decay proceeding as anticipated? Is there evidence of a secondary peak suggesting fragmentation? Updates on non-gravitational acceleration. Is the comet deviating from its predicted trajectory? Radio telescope follow-up. Has it been scanned for any emissions? Archival data sweeps. Are there any timing anomalies in spacecraft telemetry? Ionospheric monitoring. Were there any disturbances during its close approaches? Each of these measurements represents a potential thread. Pulling a single thread may yield no significant unraveling. However, tugging on multiple threads could reveal an emergent pattern, one previously obscured, a pattern that fundamentally alters our perspective. And this leads to a final consideration. 3I Atlas is not the sole enigmatic entity in the celestial sphere. It is not the only anomaly challenging our assumptions, nor the only object prompting scientists to pose uncomfortable questions. There are others. Fast radio bursts with inexplicable characteristics. Trans-Neptunian objects exhibiting peculiar orbits. Quantum experiments revealing timing residuals. AI-driven discoveries uncovering patterns previously missed by human observation. The universe is replete with loose threads, and it is conceivable that they are all interconnected, forming a single, vast tapestry. Part 11. The recurring oddities of fast radio bursts. Let us now shift our focus from comets and our solar system to the vast expanse of deep space, where pulses of radio energy emanate from the darkness. Fast radio bursts, or FRBs, represent one of the most profound mysteries in contemporary astrophysics, and in a peculiar fashion, they might be linked to the narrative of 3 Atlas. Fast radio bursts, as their name suggests, are exceedingly brief pulses of radio emission, lasting mere milliseconds, possessing immense brightness, and detectable across billions of light years. The initial discovery of such a phenomenon occurred in 2001, embedded within archival data from the Parkes telescope, though its significance was not fully appreciated until 2007. Since then, hundreds, perhaps thousands, have been detected, depending on the classification criteria. The majority are transient, flashing once and never repeating. However, a subset does repeat, and these repeating FRBs are particularly perplexing. Repetition implies a persistent source, not a singular cataclysmic event, like a supernova, but rather an entity capable of repeated emissions. This could be a neutron star, perhaps a magnetar with exceptionally strong magnetic fields, or something entirely unanticipated. Allow me to cite a recent example. FRB 22108A, discovered in 2022. This source repeats, but not randomly. It exhibits periodicity. The bursts tend to occur within active windows, followed by periods of silence and then recurrence. This periodicity suggests rotation, possibly of a neutron star with a localized emission region. When this region rotates into our line of sight, a burst is observed. This is the prevailing hypothesis. However, a significant challenge exists. The observed bursts do not perfectly align with standard magnetar models. The frequency structure is unusual, with some bursts exhibiting a frequency sweep from high to low, while others do not. The polarization patterns are complex and difficult to explain, and the energy output is staggering, equivalent to the sun's output over decades compressed into milliseconds. We are contemplating celestial bodies the size of cities unleashing unimaginable amounts of energy. Are these phenomena natural? Almost certainly. Are they fully understood? No. And this is where the connection to 3I Atlas becomes intriguing, as both phenomena challenge our established models, push the boundaries of what we define as normal, and invite speculation regarding exotic physics or even artificial origins. Consider this hypothetical. What if 3I Atlas emitted a radio pulse during its perihelion passage? A brief, powerful burst, potent enough to be detected across galactic distances, yet strong enough to be registered by nearby radio telescopes if they were precisely oriented. What would be observed? A millisecond pulse, either broadband or narrowband, potentially exhibiting frequency structure and polarization. Would it be recognized as an FRB or dismissed as mere interference? The detection of FRBs is contingent upon active searching, the implementation of specialized detection algorithms, and continuous sky surveys. However, no one points radio telescopes at comets with the expectation of detecting FRB-like emissions. Why would they? Comets are essentially icy bodies. They do not possess the necessary magnetic fields for coherent radio emission, nor do they have adequate energy sources. They are typically considered passive objects that reflect and scatter sunlight. But what if this assumption is flawed? What if, under specific conditions, a comet's ionized coma could generate radio emissions? What if the interaction between the solar wind and cometary plasma could lead to instabilities, magnetic reconnection events, and subsequent coherent radiation? These are speculative concepts, but not entirely improbable. Plasma physics is inherently complex, nonlinear, and replete with unexpected behaviors. Alternatively, adopting a more provocative interpretation, what if an FRB detected in proximity to 3I Atlas was not generated by the comet itself, but was deliberately timed to coincide with it? This would imply a signal originating from elsewhere, intentionally synchronized, utilizing the comet as a temporal marker or beacon. This is highly speculative, but such speculation becomes less far-fetched if a correlation can be established. The observational challenge lies in the fact that FRBs are detected by all sky monitoring instruments, such as SHIME in Canada or ASCAP in Australia. These telescopes do not target specific celestial objects. Instead, they survey vast regions of the sky. Therefore, if an FRB occurred in the vicinity of 3I Atlas, it would appear in the data. However, correlating it with the comet would necessitate a targeted effort to examine whether any FRBs detected in October 2025 originated from the comet's position in the sky. Has such an analysis been undertaken? It is uncertain. Perhaps it has. Perhaps it has not. But if it has, and if even a single FRB were found to coincide with the comet's trajectory, that would be an extraordinary finding. It would not serve as definitive proof, but would be remarkable because it would suggest the existence of a previously unrecognized class of phenomena, micro-FRBs, or localized FRBs, emissions not traversing the entire universe, but originating within or just beyond our solar system. Now, let us broaden our perspective. Consider the impact of observational bias. We tend to discover that which we actively seek. Chima detects FRBs because it is specifically designed for that purpose. However, it filters out signals that deviate from its established template. Signals that are too long, too short, too faint, or too strong. Its optimization is geared towards extragalactic bursts, not local anomalies. Consequently, what if an entire category of radio transients remains undetected? Bursts from comets, from asteroids, from interplanetary dust clouds. Emissions occurring when charged particles interact with magnetic fields in unexpected ways. We would not perceive them because we are not looking for them, and we are not looking because we assume their existence is impossible. This highlights the inherent danger of theoretical models. They dictate our expectations, and our expectations, in turn, influence what we observe. Everything else is relegated to the status of noise, dismissed as error or buried in archives until someone revisits the data with fresh perspectives, advanced algorithms, and novel hypotheses, at which point the noise transforms into a signal and the error into a discovery. Therefore, my question is this: should we initiate a process of correlating FRB detections with the passages of interstellar objects? Should we cross-reference their sky positions and timestamps? Should we systematically search archival data for coincidences? Because if such coincidences exist, if even a tenuous correlation is found, it would revolutionize our understanding. It would imply that these objects are not as inert as we currently believe, that the universe is far more dynamic and interconnected than our models suggest, and that 3 Atlas might be an integral part of a larger cosmic pattern, a pattern we are only beginning to perceive. Part 12. Anomalous Solar System. Object Discoveries. Let us now refocus our attention on our own solar system. While our gaze has been fixed on 3I Atlas, other peculiar phenomena have quietly accumulated within our astronomical catalogs. These include trans-Neptunian objects with unusual orbital characteristics, near-Earth asteroids exhibiting unexplained behaviors, and each instance prompts the same fundamental question: are these isolated curiosities, or are they components of a larger yet-to-be-assembled puzzle? Let me introduce you to the trans-Neptunian region. Beyond the orbit of Neptune, at an approximate distance of 30 to 50 astronomical units from the Sun, lies a population of icy bodies known as the Kuiper Belt. Pluto is its most renowned inhabitant, but it is home to thousands, perhaps hundreds of thousands, of other objects, and their orbits offer valuable insights. The majority of Kuiper Belt objects maintain orbits within a relatively flat disk. Their orbits are either circular or mildly elliptical, exhibiting stability and predictability. However, some deviate significantly. A subset possesses orbits tilted at extreme angles, while others have perihelia that bring them considerably closer to the Sun than anticipated. Furthermore, some exhibit clustering in patterns that appear non-random. This clustering phenomenon gave rise to the hypothesis of Planet 9, the theoretical existence of a massive planet, estimated to be 5 to 10 times the mass of Earth, orbiting in the distant solar system, far beyond Neptune. Its gravitational influence is thought to guide these distant objects into aligned orbits, thereby explaining the observed clustering and orbital tilts, as well as anomalies that would otherwise be dismissed as statistical aberrations. Nevertheless, Planet 9 has never been directly observed. Its existence is inferred, a spectral presence within the data. Some astronomers subscribe to its reality, while others contend that the clustering is a consequence of observational bias. We detect more objects in certain regions simply because we have surveyed those areas more thoroughly. The debate remains ongoing, with each new discovery either bolstering or weakening the underlying hypothesis. Now, allow me to present a specific example. A trans-Neptunian object discovered recently, which we shall designate as 2025 TN113. Its orbital path is exceptionally peculiar, characterized by high ellipticity, a perihelion at approximately 40 astronomical units, and an aphelion extending beyond 1,000 astronomical units. Its orbital period spans tens of thousands of years, and its inclination relative to the ecliptic is extreme, exceeding 60 degrees. How did such an orbit form? Possibly gravitational scattering by Neptune billions of years ago, flinging it outwards, or the gravitational influence of a hypothetical planet 9, or perhaps a cosmic event like a passing star or rogue planet, an encounter too ancient for us to fully reconstruct. But here's the curious part. When we map the paths of these extremely distant trans-Neptunian objects, they don't appear scattered randomly. Instead, they form clusters. Their points of closest approach to the Sun, their perihelion arguments, and their orbital tilt alignments, their nodes of ascending longitude, all show this clumping. This is highly suspicious, as random scattering should result in chaos, not order. Unless, of course, there's an unseen, massive entity out there subtly guiding their orbits. Alternatively, this alignment might be an observational illusion, a consequence of precisely where and when we've directed our telescopes. The scientific debate is ongoing, and this very discussion highlights the gaps in our current knowledge. We simply don't know what lies in those distant realms, or what forces shape the outer solar system's architecture. It is precisely within this uncertainty that the truly unexpected, the Black Swans, can hide. Now, let's draw a parallel to the object known as 3I Atlas. Both represent anomalies. Both defy conventional expectations. Both force us to question what constitutes normalcy and what lies beyond it. And both underscore deficiencies in our established population models. We once believed we had a solid understanding of comets and trans-Neptunian objects. However, closer examination, particularly of these outlier cases, reveals that our established patterns begin to unravel. We realize that normal is merely the aspect we've observed most frequently. So, are these anomalies isolated incidents, or are they indicators of a more profound, systematic phenomenon? Could there be a population of interstellar travelers we haven't yet detected? Objects that traverse our solar system regularly but are too faint or too swift for us to notice? Perhaps there exists a collection of extreme Kuiper Belt objects, shaped by gravitational encounters beyond our current comprehension. It's possible the solar system is far more complex, more chaotic, and more astonishing than our textbooks currently depict. And here's the crucial point. If these peculiar objects are part of a discernible pattern, connected by some underlying, as yet unidentified process, we won't recognize it until we accumulate sufficient data, catalog enough outliers, and until someone performs a statistical analysis that reveals a correlation. By that point, the pattern will likely appear obvious, and we'll wonder why it wasn't apparent sooner. The truth is, we didn't see it because we weren't actively looking for it. Our existing models, our preconceptions, directed us away from such possibilities. This is the very nature of scientific discovery. We find what we seek, and we overlook what we do not. The pressing question is, what are we currently missing? What patterns are lying in plain sight, and will we identify them before they become critically significant? Or will our understanding only arrive in hindsight, when it is too late to prepare? Part 13. Quantum Physics Anomalies and News. Let us venture into even more perplexing territory. Fundamental physics, the very bedrock of our comprehension. The physical constants and laws we assume to be universal, immutable, and eternal. But what if this assumption is flawed? What if the universe is less stable, more adaptable, and more surprising than we currently imagine? In the year 2024, a paper emerged on the Archive preprint server, proposing a potential anomaly concerning the fine structure constant, alpha. This fundamental constant quantifies the strength of electromagnetic interactions and is ubiquitous throughout physics, influencing atomic spectra, quantum mechanics, and electromagnetism. It is, by all accounts, expected to be uniform, the same across the entire universe and at all points in time. However, this paper analyzed quasar spectra from extremely distant galaxies, capturing light that has traversed billions of years to reach us. It detected subtle indications, extremely slight hints, that alpha might have differed in the early universe by mere parts per million. While seemingly minuscule, this deviation, if validated, would be statistically significant. The scientific community remains divided. Some attribute it to calibration errors. Others suspect systematic biases within the observational data. A contingent believes it represents a genuine and revolutionary discovery. The discourse continues, emphasizing the critical need for more data, enhanced measurement precision, and independent verification. Yet, the possibility persists. The possibility that fundamental constants are not, in fact, constant, and that the universe evolves in ways we are yet to comprehend. Now, let's shift our focus to timing residuals. Pulsars are renowned for their extraordinary precision as cosmic clocks, spinning hundreds of times per second, emitting pulses so regular they can be used for timekeeping. Astronomers utilize pulsar timing arrays to detect gravitational waves. They meticulously measure the arrival times of pulses from numerous pulsars, searching for correlated deviations. These deviations are theorized to be caused by space-time ripples emanating from distant black hole mergers. However, occasionally, these deviations do not exhibit the expected correlations. Instead, individual pulses display timing residuals that defy conventional explanation, perhaps attributed to noise, instrumental error, or interstellar medium effects. But when these residuals are exceptionally large, persistently anomalous, or strikingly peculiar, one begins to ponder alternative causes. What if space-time itself is inherently more irregular than we assume? What if there are glitches, fluctuations, or anomalies that our current models fail to incorporate? Let's connect this to the 3I Atlas scenario, and specifically to the concept of a reality glitch. If fundamental physics exhibits imperfections, if constants are not perfectly invariant, and if timing systems are less robust than we suppose, could an interstellar object passing through our solar system inadvertently highlight these imperfections? Could it interact with the local space-time fabric in a manner that reveals underlying instabilities? I am not suggesting that 3I Atlas possesses inherent distorting properties. Its mass is insufficient, and its gravitational influence negligible. However, what if it is traversing a region where space-time is already subtly anomalous? A region with a higher than average density of dark matter, perhaps, or one influenced by a passing gravitational wave. A region where, for any number of reasons, physical constants are minutely different. If such a scenario were true, instruments observing the comet might detect anomalies, timing offsets, spectral shifts, trajectory deviations that do not conform to Newtonian or relativistic predictions. This would not be due to the comet's exotic nature, but rather because the surrounding environment is exotic, and our current observational resolution is insufficient to perceive it. This is a highly speculative line of thought, admittedly venturing into the realm of wild speculation, yet it is grounded in genuine scientific inquiries concerning fundamental physics. These are questions that experiments such as the Large Hadron Collider, the Dark Energy Survey, and pulsar timing arrays are actively pursuing. The more precisely we measure the universe, the more we encounter anomalies, small deviations, edge cases, and outliers that challenge the standard model. Each outlier represents either an error or a nascent discovery. The primary challenge lies in differentiating between the two, as errors are commonplace, while genuine discoveries are rare. Distinguishing them demands rigor, reproducibility, and independent confirmation. Yet, on occasion, only a single opportunity arises, a solitary measurement, a single object passing through. If we dismiss such an event as an error, we risk overlooking a profound discovery. Conversely, if we prematurely claim it as a discovery, we risk being incorrect, a potential misstep that could be embarrassing, deemed careless, and career-ending. Consequently, scientists tend to err on the side of caution, demanding high levels of confidence, multiple lines of evidence, and reproducibility. While this approach is commendable and necessary, it also inherently biases us towards missing discoveries, towards categorizing truly anomalous phenomena as mere noise, and towards prioritizing safety at the expense of revolutionary insights. This brings us back to the central inquiry. Are we examining 3I Atlas with the appropriate tools, the right hypotheses, and the necessary openness to surprise? Or are we forcing it to fit within our existing models simply because it is comfortable and aligns with our training? Admitting our lack of understanding is considerably more challenging than feigning comprehension. I do not possess definitive answers, but I do have questions. And questions are the genesis of scientific exploration, the origin of discovery, and the foundation of understanding. If 3I Atlas serves to teach us anything, it should be this: the universe retains its capacity for surprise, and we must remain prepared for it. Part 14. AI-driven signal and pattern detection. Breakthrough. Contemporary science finds itself simultaneously overwhelmed and empowered by its own remarkable advancements. Every night, our instruments deluge us with an unprecedented volume of information, far exceeding what any previous generation could have conceived of managing. Telescopes sweep across the celestial sphere, generating terabytes of data before the break of dawn. Satellites in Earth orbit transmit continuous streams of measurements, ranging from temperature variations to radiation levels and magnetospheric flux. Particle accelerators meticulously record billions of collisions per second, each collision a potential Rosetta Stone for understanding the fundamental fabric of reality. Yet, despite this technological prowess, we cannot possibly observe or analyze it all. We cannot scrutinize every image, verify every spectrum, or parse every line of code that describes the universe back to us. The sheer deluge of data has outpaced the processing capacity of the human brain. Consequently, we resort to automation. We develop algorithms to sift through the noise, to highlight phenomena we already believe are significant. We design filters to eliminate false positives and reduce complexity. We entrust these automated systems to identify the familiar and discard the rest. But what happens when the truth resides within the discarded data? What if the signal of the century, an anomaly poised to redefine physics itself, was quietly removed by our filters simply because it did not conform to a pre-existing pattern? This is where artificial intelligence introduces a transformative element to the narrative. Machine learning algorithms do not merely execute predetermined instructions. They learn directly from data. Rather than relying on rigid filters, they adapt and evolve. They identify patterns that elude our mathematical descriptions, perceive structures invisible to our visualization capabilities, and detect deviations that defy our rationalizations. The crucial paradox is that AI does not necessarily know what it is searching for, and this very ignorance is its strength. In recent years, AI has begun to yield genuine scientific discoveries, not mere simulations or theoretical predictions, but tangible, verifiable findings. Consider the Kepler Space Telescope. Between the years 2009 and 2013, Kepler meticulously observed over 150,000 stars, recording their brightness at intervals of a few minutes in its quest to discover transiting exoplanets. The mission's primary pipeline successfully identified thousands of worlds, but it was specifically optimized for predictable, regular dips in brightness, indicative of periodic orbits and strong, clear signals. However, the universe does not always adhere to such regularity. In 2023, a research team applied deep learning techniques to the extensive Kepler dataset. They trained neural networks not on theoretical models, but directly on the data itself. The AI was not explicitly instructed on what a planetary signature should resemble. It simply learned to discern what constituted a difference. The outcome was the identification of a handful of new planets that the original algorithm had overlooked, including those exhibiting irregular or quasi-periodic transits. Instances where orbits are perturbed by neighboring celestial bodies or tilted due to gravitational resonance. The AI even detected potential exomoons, celestial bodies that induce subtle, asymmetric dips in stellar brightness, which had previously been dismissed as mere noise by human-designed code. This represents a quiet revolution in scientific exploration. AI is not replacing astronomers. Rather, it is guiding them towards avenues of inquiry they might never have conceived of pursuing. The same paradigm is observable in other scientific domains. Take, for example, galaxy morphology. The classification of galaxies into spiral, elliptical, or irregular shapes has historically been a manual process, at times even an artistic endeavor. Subsequently, initiatives like Galaxy Zoo emerged, empowering citizen scientists worldwide to categorize millions of galaxies by hand. AI, however, can analyze tens of millions of galaxies overnight. When researchers unleashed AI upon the data from the Sloan Digital Sky Survey, it began to unearth galaxies that defied all established classifications. Some bore the hallmarks of collision remnants. Others resembled artifacts of gravitational lensing or ghost images of galaxies superimposed upon others. Each anomaly hinted at novel astrophysical processes. The AI was not merely replicating human knowledge. It was actively expanding the very taxonomy of the universe. Now, imagine applying the same analytical approach to 3I Atlas, the interstellar object that has captured global attention. It is exhibiting behavior inconsistent with that of a typical comet. Its acceleration patterns are unusual. The dynamics of its tail shift unpredictably. Its albedo variations do not align with standard outgassing models. Therefore, what if we were to feed all available data concerning 3I Atlas into a neural network? This would encompass every photometric light curve, every spectroscopic reading, every trajectory log, every polarimetric profile, and every image metadata set collected from observatories worldwide. Then, we could pose a simple question to the AI. What does not fit? This approach would involve no assumptions, no preconceived models, relying solely on pattern recognition. It might detect fluctuations in brightness that repeat every 6.3 hours, a regularity too precise to be coincidental, yet too erratic for simple rotation. It might identify subtle drifts in the amplitude over time, suggesting a secondary periodic modulation, perhaps indicative of binary rotation or an active core responding to internal heat cycles. Alternatively, the AI might uncover something more profound, a correlation between outgassing jets and non-gravitational acceleration, but one that deviates from established physical principles. It is conceivable that the thrust vectors are asymmetric in a manner that implies directed emission, as if something is actively steering the ejected material rather than simply venting it. None of these findings would be conclusive on their own, but each would be undeniably intriguing. And this is precisely where the process of discovery begins. AI possesses a singular superpower. It notices. However, it also has a critical limitation. It lacks true understanding. It cannot reliably distinguish between noise and novelty, or between coincidence and causality. It flags anomalies, but it falls upon humans to determine their significance. And humans, despite our considerable intellect, are inherently biased. We crave patterns, seeing faces in clouds, divine intervention in thunderstorms, and intentionality in randomness. In science, This bias can manifest in two opposing ways. We may invent meaning where none exists, or we may dismiss potential meaning because it appears too unconventional. Therefore, the solution is not to blindly trust AI. It is to rigorously verify. This involves performing the same analysis across independent datasets, employing multiple models, and cross-checking results with different instruments. If a signal persists, if it appears under varying conditions, utilizing different algorithms and operating under different assumptions, only then can we begin to entertain its validity. Replication serves as the antidote to illusion. Has anyone already undertaken such an analysis? Has someone, somewhere, inputted the complete 3i Atlas dataset into a deep learning model? Perhaps a graduate student at JPL, or a hobbyist running TensorFlow on a home GPU cluster, or even a national laboratory conducting undisclosed projects. It's possible the analysis is occurring at this very moment, with only a small group aware of its findings. Or perhaps, astonishingly, no one has attempted it. It is conceivable that our most significant cosmic anomaly is slipping through our grasp because no one considered entrusting the machines with its examination. If this is indeed the case, it represents a missed opportunity of historic proportions. This is the future of astronomy, the synergy of human intuition and machine perception, a partnership between theoretical frameworks and empirical data. We formulate the models, the AI challenges them. We interpret the findings, the AI uncovers what we cannot even imagine. In the coming decade, with the advent of observatories such as the Vera C. Rubin Observatory, LSST, which will generate 20 terabytes of sky data nightly, relying solely on human analysis will become untenable. The universe will necessitate algorithmic curiosity. In this evolving landscape, discovery will no longer signify stumbling upon something unexpected. It will mean training machines to perceive that which we have inadvertently trained ourselves to ignore. This brings us full circle. A Black Swan event in space is not merely a surprise. It is something so far removed from our expectations that our entire framework of understanding must be reconfigured to accommodate it. But how can we detect the truly unexpected if our search is predicated solely on what we anticipate? This is the paradox of modern science. As our instruments become more sophisticated, our vision can paradoxically narrow. As we become engrossed in meticulous detail, we filter, we automate, we impose limitations. AI could be the key to breaking this cycle. Because if 3i Atlas is anything, a natural oddity, a misidentified interstellar relic, or something far stranger, it represents a test of our capacity to look beyond our established models, to search without knowing precisely what we are seeking. And if an AI someday uncovers something within its data that we cannot explain, cannot replicate, and that fundamentally challenges physics itself, that will be the most profound Black Swan of all. A discovery not made by humans actively seeking meaning, but by a machine identifying something beyond human imagination. Somewhere within a server room, humming quietly under sterile white lights, petabytes of sky data lie waiting, invisible to the human eye yet teeming with secrets. An algorithm will awaken, sift through the noise, and perhaps, just perhaps, detect a flicker that no one else has noticed. A pixel slightly too bright, a curve subtly off, a pattern that simply does not conform. And from this faint whisper of data, a question will arise. Is this merely noise, or did the universe just blink? This is the era we are entering. An era where machines observe the cosmos, not merely on our behalf, but in collaboration with us. And when the next anomaly akin to 3i Atlas appears, it will not only test our scientific methodologies, but also our ability to heed what the machines are attempting to convey. Part 15. Final Reckoning and Looking Forward. And so, here we stand. 15,000 words into an investigation of a comet that could prove to be utterly unremarkable or profoundly significant. 3i Atlas, an interstellar visitor that arrived in July of 2025, outgassed when it was not expected to, exhibited a chemical composition unlike anything we have ever encountered, passed perihelion on October 29th, and is now receding into the darkness, fading from view, vanishing back into the void from which it emerged. The central question persists. Is this merely an unusual comet, or is it a dormant black swan awaiting its revelation? Let us revisit the proposed scenarios. Orbital domino effect, plausible over decades. It remains impossible to rule out or confirm at this juncture. We will only ascertain its validity if something unexpected transpires years from now. Fragmentation event. As of now, no confirmed fragmentation has occurred, but the stresses of perihelion passage could trigger a delayed breakup. Follow-up observations are ongoing. Solar disruption. No significant solar events coincided with its perihelion passage, diminishing the credibility of this scenario. However, the underlying question remains relevant for future interstellar visitors. Artificial signal. No confirmed detection has been made. Archival searches are currently underway. While the probability is low, the potential implications are immense. Atmospheric anomaly. The situation remains unclear. Data exists, and analysis is required. Disclosure cascade. This is a possibility, perhaps subtle and imperceptible in real time. Psychological singularity. This is already occurring, evidenced by media coverage and widespread public speculation, with real-world consequences stemming from perceived uncertainty. Reality glitch. There is no evidence to support this, though it remains a philosophically intriguing, albeit wildly speculative concept. Therefore, what remains plausible? Orbital perturbations, fragmentation, and psychological effects are still viable. What has been largely ruled out? Solar disruption. Artificial signals and reality glitches, for the most part, remain in the realm of we haven't investigated thoroughly enough to definitively say no. And therein lies the frustration. The absence of evidence is not evidence of absence. Just because we have not yet detected something does not mean it does not exist. So what transpires next? What observations are of paramount importance? Post-perihelion. Brightness monitoring. Is the light curve decaying as anticipated? Are there any secondary peaks or unusual fading rates? Non-gravitational acceleration updates. Is the trajectory consistent with predictions? Are there any deviations as outgassing continues? Radio telescope follow-up. Has anyone scanned for emissions? Have any archival signals been detected? Spectroscopic analysis. How is the comet's composition evolving? Are there any changes in the ratio of carbon dioxide to water? Fragmentation monitoring. Are any new components appearing? Is there any unusual morphology visible in high-resolution images? And then, there is the extensive archival work, deep dives into historical data, AI-driven analyses, cross-correlations, examining pulsar timing data, spacecraft telemetry, ionospheric logs, solar activity reports, and fast radio burst (FRB) catalogs. The aim is to identify any potential connections between 3I Atlas and broader anomalies, searching for coincidences and patterns. Some of this work is in progress, some is not, and some may never be undertaken because the necessity for it was not recognized. This represents the tragedy of missed opportunities. Once the comet becomes too dim to observe, the window of opportunity closes, the data becomes finite, and the archives are finalized. We are left with only what we managed to capture, what we prioritized, and what we deemed important at the time. But here's the crucial point. Even if the third interstellar object, known as 3I Atlas, is entirely ordinary, and every unusual characteristic it displays can be attributed to a conventional explanation, it has still imparted valuable lessons. It has served as a potent reminder that extraterrestrial visitors are indeed a reality, and that their elemental composition could be unlike anything found within our own celestial neighborhood. These visitors challenge our established scientific frameworks and demand our focused observation. Consequently, we are compelled to develop more sophisticated systems for their detection and characterization, as their arrival is not a singular event, but an ongoing phenomenon. The first such visitor was Oumuamua, followed by Boris, and now 3I Atlas represents the third. It is anticipated that many more will follow, perhaps numbering in the dozens annually once our observational capabilities are enhanced, possibly reaching one per month or even one per week. Each of these celestial travelers will possess unique attributes, offering insights into their parent star systems, the prevailing conditions of interstellar space, and the diverse mechanisms of planetary formation across the Milky Way galaxy. Furthermore, some of these visitors might prove to be black swans, objects that defy all existing categories, shatter our current models, and compel us to fundamentally revise our most basic assumptions. These could be entities that are artificial, intelligent, or indicative of physics principles we have yet to uncover. While the probability of encountering such phenomena might be low, it is not zero, and even a non-zero probability is sufficient for the possibility of a black swan event. Considering the implications, if 3I Atlas turns out to be a black swan, what would be the scientific ramifications? It could trigger a paradigm shift, introduce new physics, and lead to a profound reevaluation of our understanding of cometary activity, interstellar objects, or entirely unforeseen phenomena. From a practical standpoint, our approach to planetary defense would need to be reassessed. We would begin to track interstellar visitors with greater diligence, invest in superior detection technologies, and foster international collaboration. Culturally, public perception would undoubtedly evolve. Space would be perceived as less predictable, less secure, more enigmatic, and deserving of both cautious respect and profound awe. However, if 3I Atlas proves not to be a black swan, but simply a peculiar comet, what then? We would gain a valuable lesson in humility, recognizing that the cosmos is replete with statistical anomalies, that rarity does not equate to impossibility, and that peculiarity does not necessarily imply artificiality. We would refine our existing models, broaden our scope of inquiry, and improve our ability to discern between genuine anomalies and observational errors. Crucially, we would then be better prepared for the subsequent arrival of another object, and the one after that. In either scenario, we emerge as beneficiaries, acquiring knowledge through the scientific process. Science's inherent function is to transform uncertainty into understanding and to convert mystery into comprehension, not through instantaneous revelation, but through incremental, persistent progress over time. My concluding thought is this: if the celestial sphere can still evoke such profound surprise, if an interstellar comet can ignite such extensive speculation, rigorous analysis, and a mixture of wonder and apprehension, then what other phenomena have remained concealed from us? What other observations have we overlooked? What other anomalies lie dormant within our data archives? What other patterns are awaiting discovery? How many other black swans are currently circling, invisible, until the precise moment of their arrival? We exist in an era where advanced telescopes meticulously survey the entire firmament each night. Satellites continuously monitor our planet, and experiments delve into the fundamental fabric of existence. We possess an unprecedented volume of data, an array of sophisticated instruments, immense computational power, and an enhanced capacity to detect the unforeseen. Despite these advancements, we continue to be surprised, perplexed, and faced with questions that elude immediate answers. This reality should both inspire us and instill a sense of urgency for it signifies that the universe is far from finished with its revelations. It implies that our current models are incomplete and that discoveries, akin to black swans, are poised to emerge, events that will necessitate the rewriting of textbooks, the recalibration of paradigms, and a fundamental alteration of our perceived understanding of reality. 3i Atlas might indeed be such a transformative event, or it might not. However, the very fact of our uncertainty, the necessity of considering such a possibility, is inherently significant. It signifies that we are finally beginning to acknowledge the unpredictable nature of the cosmos with the seriousness it deserves. We are finally conceding that despite our extensive network of satellites, telescopes, and exploratory missions, space remains largely unknown, profoundly mysterious, and capable of delivering unforeseen impacts. If this realization does not compel you to gaze at the heavens with a sense of wonder and inquiry, contemplating what lies beyond, what is approaching, and what we might have already missed, then you have not been paying adequate attention. The message conveyed by 3i Atlas is not one of impending doom, but rather that the cosmos is dynamic, observant, and brimming with possibilities that are currently beyond our full comprehension. Therefore, continue to observe, continue to question, and continue to wonder, for somewhere in the vastness of space, another celestial body is making its approach. Another anomaly awaits discovery. Another black swan is silently navigating the darkness. And when it appears, when its presence is finally revealed, a single question will likely arise. Did we anticipate its arrival, or were we looking elsewhere?